we're now going to take the math that we derived in class problem 3, and in this problem we're going to apply it to an actual chemical process, or to a chemical process. And so what we're dealing with in problem 4 is we have a gas that has a heat capacity that's described by this relationship, and it's also going to follow the van der Waals equation of state, right, where this A parameter, the attraction parameter, we're actually setting equal to 0, and the molecular volume parameter we're setting to an actual finite number. All right, and so we have this gas, and what we're doing with this gas is we're having it flow through a throttle valve, right, where the inlet pressure is 10 bar and 30 degrees Celsius, and then it's going to leave the valve, the outlet, at 1 bar. And what this problem wants us to figure out is what is the exiting temperature. Okay. All right, and so based on this problem description, what I want you to do now is pause the video and draw a schematic. Based on the information in this problem statement, we could draw a schematic that looks like this. And so for our system, we're going to take a basis of 1 mole per second for the inlet flow rate. And the heat capacity can be described as 7/2 R. For the inlet, we have 1 mole per second coming in. It's at a temperature of 30 degrees Celsius and a pressure of 10 bar. At the outlet, we're told that outgoing pressure, which is 1 bar, technically we don't know the outgoing molar flow rate, but what we want to figure out in this problem is what is the outgoing temperature of the system as well. All right, and so, we've looked at valves before, and as you could probably anticipate, is that for this system, we're going to get an isenthalpic result. And so when we were dealing with ideal gases going through the valve, that result was very easy. But here we're going to be dealing with a van der Waals gas, and we're going to see that our result is going to be different. In any case, what we have are two unknowns. And so we need two equations to solve for N2 and T2. For our analysis, we're going to make a couple of assumptions. First, the problem statement told us that this is a steady state system, so we'll assume steady state. We'll ignore any changes in kinetic and potential energy. With valves, commonly we assume that they're going to be adiabatic, just because the time it takes for the gas to pass through the valve is much shorter than the time it takes for heat to actually transfer out of the valve. That's what really the physical justification for that assumption. In any case, we'll assume that this valve is adiabatic, and of course there's no moving parts, so we'll say that there's no shaft work as well. Okay? Alright, and so based on those assumptions, we could go to the material balance. A equals I minus O plus G minus C. No reaction. Steady state. Therefore, our inlet, which is N1, is equal to our outlet, which is N2, which I'll just call N dot, and that's 1 mole per second. So fairly straightforward material balance. Let's now go to our energy balance. And here, we're dealing with an open system, so we'll use the open system energy balance. This is shaft work. And then we have our inlet enthalpy and our outlet enthalpy. We're at steady state, so the entire left-hand side goes to 0. We don't have any heat. We don't have any shaft work. Right? Both N1 and N2 are just equal to N dot. In fact, we could factor that out and divide 0 by that. And so in the end, what we get is that the inlet enthalpy, molar enthalpy, is equal to the outlet molar enthalpy. Right? So this is a result that we've seen before when we have done valve analyses. Okay? And so as I hinted at before, previously when we dealt with ideal gases, we always treated enthalpy as only a function of temperature. Okay. And so if the enthalpies were the same, what we got was that T1 was equal to T2. Right, so this is what we got when we were dealing with ideal gases. And when we were dealing with steam table problems, though, we saw that we could have differences in temperature. Okay? And so what we're going to focus on in this problem is to demonstrate how, if we're dealing with actual real gases in which the molecules can interact with one another, how we could show that the temperature is going to change even though the enthalpies are the same. Okay? So now we're dealing with a van der Waals gas. So we need to figure out how T changes. Okay. All right, so that's what really the newest step in the problem is we want to figure out how the temperature in our valve is actually going to change as it passes through the valve. In this problem statement, or in this problem, we're given information about pressure and temperature, right? For the inlet and the outlet, we have pressure and we want to know temperature. And we also know from our energy balance that the enthalpies are the same. Okay? And so, since we know P and H for the inlets and outlets, what we could do, what this points us in the direction of doing, is that we want to write or think about how the temperature, we want to write it as a function of that molar enthalpy and pressure. Okay? All right, so that's how we need to think of this this problem. And so if we're saying that temperature is going to be a function of enthalpy and pressure, if we took the total derivative of it, it would have this form. Right? This is just the definition of a total derivative of a function. Alright, so that's just the math. But now let's start applying, let's actually apply the context of our chemical process. What are the actual physics of the system? We saw from our energy balance that the enthalpy is the same at the inlet and the outlet. So we have an isenthalpic system. And so what that tells us is that the dH here is going to be equal to 0. And so what we're left with is that the change in temperature, that dT, is merely just equal to dt dP at constant enthalpy. Right? And if you remember from problem 3, what we dealt with was this partial derivative exactly. Right? And in fact, we gave this partial derivative a special name. This was the Joule-Thomson coefficient. Okay? And so what we could do is we could take our result from problem 3 and just plug it directly into this into this partial derivative. So we get dt is equal to temperature, pressure, CP, dV. Okay. All right. And so if we want to figure out temperature, the temperature of the outlet stream, all we would have to do is integrate this total derivative from T1 to T2, and then integrate the right-hand side from molar volume 1 to molar volume 2. Okay? And then once we do that, then we could rearrange the equation so that we would just have T2 is equal to stuff on the right-hand side. Okay? So that's going to be the basic strategy for the problem. Right? And so what we need to do now before we do that is we still have a partial derivative in here, right? And so what we have to do is we need to figure out, how we could actually write this partial derivative in terms of, pressure or volume and temperature. It's a partial derivative with respect to those things, but we want something that we could actually plug into the equation. All right, and so to do that, that's where we go to our equation of state. That's where we apply our equation of state information. All right, and so for this problem, what we're assuming is that our gas follows the van der Waals gas equation of state, which, as you've seen before, has this form. Okay? All right, in this problem, though, just for this specific problem, once again, B is the basically the volume of the molecules, of each individual molecule, and then A is a parameter that quantifies the interaction strength between molecules. But in this problem, we're kind of dealing with a hypothetical gas in which the A parameter is equal to 0. And so physically what this would mean is that there would be no sort of no attraction between molecules. And so you could think of it as if we just turned, like flipping a switch. And in this problem, we just turned off attractions between molecules. Okay? It's not, not the most physical thing, right? This is kind of like thinking about an ideal gas, right, where the molecules don't interact with one another. But for this problem, we're doing it this way because it's going to make the algebra a little bit easier, and will at least demonstrate more clearly to you how you actually go through the math of this problem, okay, without making it too difficult for the first time through. In any case, if our A is equal to 0, then our van der Waals gas equation of state simplifies down to this. If we go back and take a look at our Joule-Thomson, or at our total derivative for temperature, what we want is we want to take the partial derivative of volume with respect to temperature at constant P. Okay? And so, right now we have our equation as P is equal to stuff. What we want to do now is we want to rearrange it so that we have it as V is equal to stuff. So if you just go through the algebra, you'll get that V is equal to RT over P plus B. Okay? All right, so because we turned off the attraction term, that made the algebra much easier. Okay? All right, so if we get that V is equal to that, if we take the partial derivative of V with respect to T at constant pressure, it's just equal to R over P. Okay? Now that we have that partial derivative, we could go back to our total derivative for temperature, and we'll just plug in. Okay? So for our total derivative, we have T times dV over dt. So now we're just going to write R over P. And then that is going to be minus the molar volume, which we have written here. T over P plus B. All right. And so all of this is with respect to pressure. These terms are going to cancel. And what we're left with is that our total derivative for temperature is just equal to B over Cp dP, where B and Cp, based on the problem statement, we're told that these are just constants. All right, so our differential equation that we need to solve becomes very simple. This is a separable equation, and so what we need to do is just integrate dt and dP. And what we get is T2 minus T1 is equal to negative B over Cp at P1, P2 dP. And so this is going to be just P2 minus P1. Okay? Alright, and so if we want to solve for T2, T2 is equal to T1 minus all this stuff. And if we plug in, so 303K minus 150 centimeter cubed per mole. R was 7 half, or CP was 7 halves R, so we're dividing. And the gas constant I'm going to use is the one that has like bar and stuff in it, because I want to cancel out the bars of the pressure. P2 is 1 bar, P1 is 10 bar. And so what we get is that as this kind of hypothetical gas passes through the valve, we see that its temperature goes from 303K up to 307K. So we actually see that the temperature of the gas increases as it passes through the valve, right? And so, for an ideal gas, we saw that temperature wouldn't change or shouldn't change. But for the van der Waals gas, in the case where attractions are turned off, we do see that temperature changes.